Well, welcome everyone to another lecture talk from Space Society Twente. We're glad to see you here, and hopefully more people will be joining us as we go. So today we have a very interesting talk about the Lunar mission that is presented by Marc Klein Wolt, who is the director of the Radboud University Radio Lab. And this talk will also include some cultural exchange slides, which seem to me as a very nice addition to our engineering curriculum. But I'll let Marc do the talking from now on. So please enjoy the talk. And Marc, take it away.
Well, thank you very much, Higan. So good evening, everyone. My name is Marc Klein Wolt. I'm the director of the Radboud Radio Lab at the Radboud University in Nijmegen. I'm going to talk to you about a project that we started beginning of 2016, or actually end 2015 already, and that's currently flying on a Chinese satellite behind the moon. It's called the Netherlands-China Low Frequency Explorer, or NCLE. It's a payload on a radio payload on a relay satellite behind the moon, part of Chinese Chang'e 4 mission. So I'll talk about a little bit about the science behind this. So why do we even go to the moon? I'm going to talk a little bit about the Chinese space program and some of the recent developments. Some cultural aspects, as we already discussed, and then I have a little bit of an overview on how we made the actual instrument. So mind you, I'm a scientist. I'm an astronomer, so I'm no engineer. So if you come with really technical issues, then maybe I cannot answer all your questions. On this mission, or on this whole project that is actually still ongoing, I was followed by a journalist for about 3 years. So there's an actual podcast. It's in Dutch, but there's an actual podcast on this, which deals a little bit with the struggles that we had as a project while being in China, and while actually learning how to deal with some of these cultural differences that we were experiencing. And maybe if you're interested in that, then I can advise you to find this podcast in one of your podcast platforms. So I thought I'll start off with a little bit a quick background on the Radio Lab and the University of Nijmegen. So we are one of the universities in the Netherlands that have a department in astrophysics. So there's Groningen, Amsterdam, Leiden, and Nijmegen. And we work together with institutes like ASTRON, which is the Institute for Radio Astronomy, and ESSON, which is the Space Research Institute in the Netherlands. We are collaborating also with the ESA, and then there's NOVA, which is the overarching astronomical, let's say, organization that coordinates much of the research that we do. So our radio lab is a modest lab with about 15 to 20 people. We are part of the Faculty of Science and embedded in the Department of Astrophysics. And my team exists of people with various backgrounds, mostly engineers, software, hardware, electronics, system engineers, project managers, all with let's say, a love for astronomy and space. So what we do in the Radio Lab is we build instrumentation for science. And we have some facilities at our university: optical telescopes, radio telescopes, test facilities where we test prototype antennas, for instance, and we have a lab available to actually build and design and test some of the hardware that we make. But we also collaborate a lot with other institutes. For instance, we don't have a clean room yet, so for that we have a partner to work with. As I said, we build instrumentation. The project I'm going to talk about is the Chang'e 4 mission, but we do a lot of other projects as well. Although we are still a small team, we are involved in many, I would say, high-profile projects. And I think maybe the project that you may have heard about that we're also involved in, me personally also as well, is the first ever image, historical image of a black hole that was released almost, let's say, over a year ago. So we built much of the software for that project, my team did, and myself, I'm involved in establishing a new telescope for that project in Africa, which we call the Africa Millimeter Telescope. So the Chinese lunar program. So we are on the Chang'e 4 mission, which is number 4 in the sequence of Chang'e missions. And Chang'e is the lunar goddess that ascended to the moon. There's a really nice Chinese story about this. And originally, the Chang'e 4 mission was actually, the Chang'e 5 mission was actually planned before the Chang'e 4 mission, but there was a rocket explosion. The Long March 5 rocket exploded for that, and that actually pushed that Chang'e 5 mission back. And that was actually launched in November 2020 and landed on the moon, on the near side of the moon in December 2020. We were launched in 2018, and this whole sequence of launches, and also the ones that are coming after that, 6 and 7, are all aimed at building facilities at the moon to do science and also to do exploration. And the end goal for the Chinese is to put a facility and to put men on the moon. So we are part of that. So this is the image of the goddess, the moon goddess Chang'e, which is a symbol for the whole program, the Chinese Lunar Exploration Program. Now, the Chang'e 4 mission is really a backup of the Chang'e 3 mission, where you see here the rover and the lander that landed already some years before. So this whole Chang'e 4 was let's say an extra mission that they could execute because they had backups of this, and for that they decided that they want to do something very ambitious and land on the far side of the moon with a lander and a rover, which they did, but also to explore international collaboration. And this is the reason why we were invited also to have an instrument on the relay satellite. Yeah, this is some images from late last year, in November actually, where the Long March 5 rocket went up to in the direction of the moon and launched the lander that would go to the near side of the moon. And this was quite a spectacular event, and I think it's one of the first time when the Chinese are quite open in terms of communication at the moment itself for any of their launches. So usually, and this was the case also for Chang'e 4, there's no live feed. You cannot follow it anywhere. You just have to rely on, let's say, inside information you get. And this time it was actually possible to have a live feed, and they shared this with the world. They're quite confident that this would work, and this, I think, is the first time for the Chinese to do it like this. This Chang'e 5 mission was a sample return mission. So a lander went to the near side, collected lunar material, and brought that back successfully to Earth. And that's quite a spectacular thing. And at this time, let's say late last year, the Chinese were operating 2 instruments on the moon at the same time, one on the near side, the Chang'e 5 mission, and one on the far side, the Chang'e 4 mission, where we are involved. And I think that is also quite unique. I don't think any other country has done that simultaneously. This is just showing where the Chang'e 5 mission landed in comparison also to, for instance, the Chang'e 3 mission and the other missions that went in the past, the US missions and the lunar missions from Russia. And you can see that the Chang'e 5 actually went to a quite unique location. Images from that mission are quite spectacular. As for Chang'e 4, I would say, bringing images that we've not seen before. And I particularly like this one, where you see the camera image of the lander as it was on the near side of the moon. Also, this is maybe quite a confusing image, but here you see the ascender, so the part of the lander that was on the near side that took off again to go back to the Earth, and you could actually follow this live. I took this image just from the screen, and this is amazing that they actually showed this all more or less live, where you see the ascender going back to Earth, taking with him the samples that it collected on the near side. And here you saw the sequence of events that actually took place that early December in 2020, which is actually quite complicated. It's not only, this mission is quite complicated. It's not only landing on the near side of the moon, collecting samples, and then ascending again, but actually doing a rendezvous with an orbiter, and then flying back to the Earth, and then disconnecting from that system and then landing again on Earth. And they all did that quite successfully. I think that's quite an achievement when you think about this. So I built in a couple of question breaks in case we have any. So this is the first one. I just discussed a little bit the Chinese lunar program, explaining to you that the Chinese are well on their way of on doing scientific and human exploration on the moon. And up next, I'm going to talk a little bit more about the Chang'e 4 mission itself and how we collaborate with China. Are there any questions already?
Well, I think people just need a little bit of time to catch up with the stream delay as well. But I have actually a small question. Because obviously the Netherlands and China are quite far apart, and you said it yourself that the Chinese mission is quite conservative. They don't really, let you show anything. So how come that they actually contacted Radboud University for an instrument on their lander?
Yes. Well, it's actually one of the things I will discuss in the next slide. So thanks for that question. And you actually see the answer to that question in the picture here, where you see the Chinese president and our king and queen on a trade mission in October 2015. And during that trade mission, there was an agreement between the Netherlands and China on peaceful collaboration in space. And one of the topics that was selected is radio astronomy. So what the Chinese wanted is to try out international collaboration. And they realized that when you are close to the moon or behind the moon or on the moon, then that the best science you could actually do is the radio science at the lower frequencies, which you cannot see, cannot hear from Earth. And I know that the Netherlands has a very huge reputation in terms of radio astronomy, so that's why they contacted us. So it was because of this trade mission. So that's the answer to that question.
All right. Well, yeah, I got a little bit ahead of myself there, but I think
that's okay.
that's a good answer. I don't think I see any questions in the chat yet, so perhaps we can just go along and maybe at the next question break we're going to get some more.
Good. I'll just continue then. So for us, this mission is quite successful, quite exceptional, and I'll talk a little bit about the science and why we want to do this. But we have been thinking about bringing an instrument to the moon or behind the moon for a very long time. So I would say close to 10 to 20 years, and before that. Other people already were thinking about these ideas, but then, I think the cost of bringing stuff to space was even higher than it is than it currently is. So we were quite pleased with the chance that we were given, and for us it's also quite a remarkable mission because it's the first ever Dutch contribution to a Chinese mission. It's also the first, or I would say, unique contribution to the first landing on the lunar far side. So we are on the relay satellite, which is in the L2, the second Lagrangian point in the Earth moon system, which is some 46,000 kilometers behind the moon. But it's that instrument or that relay satellite is part of the first ever landing on the lunar far side. So we, as the Netherlands, take part in that whole mission. It's also a first contribution to any lunar mission from the Netherlands. So I think also that's quite spectacular. And we are attempting to measure for the first time quite unique signals from the very early universe, and I'll get back to that. And there's actually one other first which I can add to this list, because after the successful deployment of the antennas that took place almost a year ago, the Chinese claimed that this satellite, the Chang'e 4 satellite, is not only a relay satellite, but half of the month it is also an observatory. So we are at this moment in time operating an observatory at the far side of the moon, the only observatory at low frequencies in the world, maybe even in the universe, but who knows. So the Chang'e 4 mission, as I said, it's still far away from behind the moon, 64,500 kilometers in the second Lagrangian point. And the second Lagrangian point is, as some of you probably know, is the point where all the sum of all the forces cancel out. So it's a kind of equilibrium point. At the point itself, it's very difficult to maneuver. If you want to stay exactly at that location, that's quite difficult. You can see that in the image, that only a small disturbance to your position would lead you to maybe drift away completely from the whole system towards the right, or fall into the potential well towards the moon. And you can see that for instance, the point that is even more unstable is the first Lagrangian point, because you have the potential well of both the sun and the moon very close by. So these are, especially that L1 point, is a saddle point, which the way you call it, they're quite unstable. But actually, it's very good possible to have a decent orbit at these around these locations, and that's exactly what they have done. They've put the satellite in a what they call a halo orbit, orbiting around the second Lagrangian point, and at that point in time it almost always has contact, direct visibility of the Earth. This is of course for communication arguments, and it also sees the far side of the moon all the time. Now remember that in the rotation of the moon around the Earth, the moon is basically fixed, so it's always facing the same side to the Earth, and of course the L2 point, which is an imaginary point, moves with the moon. So the satellite is always at the same location in this orbit behind the moon, always sees the far side, and can therefore relay communications from the far side to the Earth and back. And our instrument is on this satellite. Now, I want to go in a little bit into the collaboration with Chinese partners, so with China in general, by explaining a little bit maybe some of the cultural differences between the Netherlands and China. And one of the first things that I noticed was that it was quite difficult to get a good feeling of all the different organizations that were involved on the Chinese side in this mission, and who was actually responsible for what. And that has to do with many different things, why that is not so visible, but we try to have this overview. This is what we created at some point. And the complication comes into the fact that there's all these different teams, management teams, science teams, technical teams, that all are responsible for a different part of this relay satellite. But we had just one point of contact, and that was the National Astronomical Observatories in Beijing. So any question that we had or any information that we needed always had to go through this NAOC, and they would then distribute that over the network, and then you would hope that at some point you will get an answer. And that's a quite cumbersome way of collaborating. But this had to do also with the fact that, as I said, the Chinese were trying out this international collaboration for the first time, and they identified on the Chinese side a point of contact, and that point of contact was almost the only one that could directly talk to us and provide official information to us, which in the beginning was quite limited, I have to say. So this is just to give you an idea on how the let's say how the network was of Chinese partners. To explain the difference between Europe, the Western world, and maybe China, I make use of a series of images, and I produced even a few of my own, from Yang Liu, who is a German journalist of Chinese origin, and she made a series of these pictograms, and which she called East Meets West. It's a website and even a book that you can order that explains a little bit the differences between these, let's say, I would say cultures. There's of course very simple ones which we can all imagine. So how do we see each other? In the blue is how we see the Chinese. On the right hand side is how the Chinese see, in this case, the Germans. And you can see obvious differences, which you immediately encounter also when you go to China. This is let's say the perception that you have, but it's of course also so most of the things that you see: Chinese drinking tea, Germans eating bratwurst. So it's also difficult to get rid of these perceptions in your mind. But it goes a bit further than that. And there's a lot of these pictograms, and I try to highlight the ones that have had a direct effect on the way that we collaborated. Now, one of the things that immediately was very obvious is that we in Europe, we have a personal opinion. What we say is usually also what we think. In China, that's not always the case. So they may think something else, but they speak the collective opinion. And this means that if you talk to an engineer that had, an assignment brought to him from above, then whatever he says is that message. That is the collective opinion that is decided by the man in charge, whoever that man may be or woman. But that's what they do. It's a collective opinion, even when they think something else. And sometimes you see that in a collaboration, that they actually think something else, but they say the other thing. And that's, if you don't know this, it's quite difficult to have a collaboration or a discussion on, for instance, something that went wrong. And you're looking for, let's say, a reason why, in terms of engineering, for instance, a test didn't work. Then you will get a collective opinion, which is that's not very helpful if you want to find the source of your problem. Well, the way that we see this of course, this collective opinion is also the way that we see ourselves in Europe versus the way people see themselves in China. They are part of this collective, and we see ourselves as individuals that can also be part of a larger collective, but usually we see ourselves still as an individual in that group. And that's quite different in China. And that difference is actually enormous. So I of course, met a lot of people and tried to understand the culture and talked to a lot of people, read a lot of books about this. But when you're in China, this is also what you experience. People feel part of this collective, of a larger force that is driving everything. And that is really completely different from the way that we see ourselves in Europe, where we can strive for our own successes, where in China you strive for the collective success. So the image that we have of ourselves could actually be quite big. Depends on your own ego, of course. So I'm not saying this represents me, but certainly there's always a difference in the way that the Chinese see themselves as they always think of themselves as much less significant. I think that's the best way to describe it. Part of a bigger thing. And the funny thing is that for instance, the way we see ourselves, and I think also the way that we think, it revolves around ourselves, is also seen in the way that we work, and especially in the Netherlands, where we try to be less hierarchical. You see that the boss in the team is someone who stands out, but is at the same level as the rest of the team. Whereas in China, the boss is the boss, and he speaks, and then you're silent. And it goes a bit further even. When you are, for instance, in a meeting in China and the boss is there, then the people below him will not say anything unless they're asked to speak. And that's completely different from what we are used to in Europe. The boss can be there, sometimes he's silent, sometimes he speaks out, but he can let his team do the talking. In China, that's not always the case. So that's also quite a difference in the way that you communicate and collaborate. Well, I already said something about an opinion. We can be quite straightforward. I think we Dutch have even a reputation of being too straightforward. So I think that's depicted on the left-hand side. In China, also because the opinion should be a collective opinion, you maybe get into a little bit of a fight with yourself. So sometimes the opinion that someone is sharing with you is quite complicated. And I think that's something that you notice a lot in discussions, especially also, again, if you have technical issues, then it is sometimes helpful to be straightforward, because then you get to the issue quite quickly. And if you're not, then this complicates things a lot. And then there's the problem of dealing with problems that we are, again, straightforward, and we tackle problems that we see, especially in space industry. When there is an issue, all the attention goes to the issue. We try to find out what is the root cause of the issue and then come up with a solution. Well, finding the root cause means going back to what went wrong and finding maybe out who did something wrong or where did something go wrong. It's not always to blame people, but to learn from your mistake and then correct for it. In China, when there's a problem, the best thing to do is not to talk about it, because you cannot lose face. Because if you attack the problem and find the root cause, there will be someone who will be responsible for that, who can lose his face. And as most of the time the boss in the team is the main responsible, he will lose face. And letting your boss lose face is something you can never, ever, ever do in China. So usually problems are avoided. This has a positive side as well, because where we may sometimes have the tendency to look back too long and try to find a root cause even when it doesn't work, the Chinese have a very, I would say, positive view on things and want to look forward and just come with an alternative solution. And that requires some flexibility. And I'll get back to that. Networking. We consider ourselves in Europe to be quite a networker, I think. At least, let's see, also maybe the image I have of myself and of my colleagues. But in China, it is even more extreme, I would say. I was going to say worse, but it's not worse, it's extremer. And the reason for this is that having relationships at all levels, especially up at higher levels, helps you to understand exactly what is going on. And this is, of course, also inherent to the, let's say, collective aspect of working as a team. As you can see on the left-hand side, you are singling out small groups in a larger collective. That is, of course, not the case in China, where everyone is connected. So that's really part of the way they work. But they also expect you to have that same kind of relationship at all levels on our side. So where I had to also find the right connections in China during my project, at the same time, I had to make sure that I had also such an elaborate network on our side in the Netherlands, up to the level of politicians, to make sure that there's a connection possible at all these various levels. So this is exactly what we depict here. that networking on all levels is really difficult. And I think there's a few things that are important here. And the first thing is that all information goes from bottom to the top. So when you want to make a change, for instance, when we wanted to make a change in our design or change something in the collaboration, we had to start at the lowest level, at the scientists and the engineers that we were working with. What that then happens is that they take that message and basically wrap it so that it can be transferred to a higher level. So you use that enormous network to make sure that the information reaches the top. And then you have to realize that there is always what I called a hidden layer, a layer of let's say, management or organization that you don't always see. And that can be there can be various reasons for it, but in my case, the reason for it was that the Chinese Academy of Sciences, or in more particular, the Chinese Space Organization, is a military organization. So there are certain layers of let's say military officials who are not allowed to talk to us or have direct communication, and that always has to go let's say through lower layers. So the actual people that you talk to, even when you feel that you're at the highest level, are sometimes not the people who decide what is happening, and that's really difficult. But what I tried to do in my project is to make sure that we had enough connection up to the highest possible level. I'm not sure if I reached the actual top, but at least I tried to have connections at possible levels, and this was the highest possible level. And it was, for part, it was possible also because of the let's say the royal intervention on our side and the fact that the Dutch government was supporting this. I got a lot of support, for instance, from the Dutch embassy in Beijing. That they are the ambassadors and people in the embassy can sometimes be at the level of ministers in terms of hierarchy. So that's quite high up. So I'm not sure if we reached the total top, but this certainly helped. So then a few of these concepts of losing face, that's really important in China. They have special, or have a few characters explaining this. There's actually a variety of characters that do that. So they have a couple of words to describe face or losing face. But it's really much worse than what we have in Western cultures. If you lose face, it really has an effect on you personally. It can have even an effect on you, on your career, on your reputation, and your social standing. So it can have long-lasting effects. So you have to make sure that you don't get into a position that you lose face, or also that you make sure that, for instance, your boss, your supervisor, also doesn't lose face. And in that respect, it's good to give face to someone, which sounds a bit strange maybe, but any solution that came from the Chinese side, even though it was maybe sometimes designed or thought of by the engineers at a lower level, they would immediately give all the credits to the boss that probably was never involved in all this decision making or in this creative process, but he would always take that and use it for his reputation, which, you know, is something, if you know that it works like that, is not a problem, but you have to know it. So this is what I said, you have to give the credits to your leader. And yeah, also there's a lot of gifts involved, exchanges in these kind of collaborations, where you give credits to the supreme leaders in China, to their efforts, and that sounds a bit funny. It's not something that I always was familiar with in previous collaborations, for instance with France or with Germany or the US even, or in Africa. But in China this is very important, but it really helped building up relationships And the good thing about these kind of relationships, if you do it like this, is that they're quite long lasting. So it's not, so it takes a lot of time to build it, but once you have it, that relationship, it is still there. For example, I mean, we started this project in, as I said, in early 2016. Last Friday was the Chinese New Year, and I'm still in contact with the highest boss of the Lunar space program. And I send him a message, and he immediately responds back in a very friendly way. So it is, I'm still, let's say, on the speed dial there, even after all those years. And I think that's also because of this effect. Yeah, and then losing face has also some good consequences. It's good to know that you cannot lose face. That means that, for instance, a contract discussion on agreements and the signing of a contract in the West would be something that is considered the end point of negotiations and maybe the start of building the actual design that you decided upon. In China, usually the signing of the contract is still seen as a continuation of the negotiations, and they will actually happen as well. So the deadline is in that sense never fixed. A decision is never really set in stone. But the good thing about that is the flexibility. And that's proved a number of times in this project to be very valuable, even up to the point that when we delivered the hardware to the clean room close to the launch site, at the launch site actually, we found out there was a small change in the design on their end that would normally mean, let's say, for instance, at ESA or in NASA, would mean a complete failure of the mission because there was an extra wire there that nobody knew about. At least we didn't, and we thought this is the end. This is not. I mean, with that wire there, we could not mount our instrument on the panel of the spacecraft. But it took half an hour of discussions with some of the engineers that were present. And at some point, somebody just came, cut the wire, and rerouted it, just like that. And I remember the face of my sister engineer looking at this. He was complete awe, like, how can this ever happen? I mean, especially when you do something like this at ESA, you have to go and work through a lot of paperwork before you can make this happen. So the flexibility is also very good. So one of the things that you can do to prevent losing face is being flexible and having various different options at the table. And that means that where, for instance, the way that we work in Europe in space programs is we consider various options at an early stage, but then decide on the one option that goes through, and that's the option that goes through. And we spend a lot of work making sure in terms of calculations and simulations and whatnot to make sure that the risks are under control or have a mitigation so that the success is guaranteed. In China, the way to guarantee success is keep various options open and maybe even do things in parallel. Of course, there's a power in number here as well, as the Chinese have a little bit more manpower to do also these kind of things. Again, question break. We discussed a little bit of this collaboration with China, and next I'm going to dive in a little bit into the science. Any questions at this point?
Yes, actually, I think people have warmed up a little bit, so we have a few
Good.
questions. First, we have a small shout out to Martin Ferson, who says that he's just joining the stream and he's your colleague from Radboud University. So he says hi, and he says that he completely agrees with the collective opinion bit of the Asian culture.
Thank you.
We also have a question from Sebastian, and the question says basically, with increasing tension between China and several other Western countries, do you see these kind of collaborations happening again, regardless of the fact?
That's a good question. If I only knew the answer. I can tell you what I would like. Maybe I'm going to try to answer the question. I think it will be more difficult. I mean, if these tensions continue to grow, then I think it will be more and more difficult. And as a matter of fact, we are experiencing these difficulties already currently. So in the Netherlands, during my project, the sensitivity with China, with respect to China, or maybe the fear of China stealing information and all these kind of things has grown a lot. So there's a large, I would say, even national discussion happening at this point in time. I think just the other week there was a remark, or it was an item in the news that the minister, education minister, is going to look at the collaboration that the Groningen university professor has with a Chinese institute. All those kind of things, you see them popping up a lot, and people are more careful about this. Now, my personal opinion is that we should be careful in collaborations always, whether it's China or the US or France or Germany. We should always be careful. And what I try to do in this project is be realistic and make sure that we give a little, but we receive a little as well. So you have to try to find a balance in this. And I think that is very difficult to do sometimes. But to give you an example, in my project, it was very clear from the start that we would get a launch to the moon. Now that's quite, substantial thing to get, especially when you're already working on this for 20 years and not even our own space agency ESA was able to give us that ride to the moon, but the Chinese could. So we realized we had to give something back to them. And I think it was clear from the start that the Chinese wanted to learn more about this kind of science. So how do you do radio science in space? What kind of science do you do? So for us, scientific collaboration with China or the US is a thing we can share. So there's no mysteries there, I think. That's something what we do as a university. It's the core of being a scientist. You share, you collaborate, and then you learn together. But there was a few things that I did not share with the Chinese, and that was mostly some of the electronics designs, especially from the parts that we got from companies where, that were partners in this project, because that's their IP, their knowledge that I didn't want to just give to China. And the other thing was the knowledge on how you actually do the detailed analysis of the science data. So we can collaborate on the science and we can do the investigation together, but it was part of the software that actually deals with how you, let's say the details of how you deal with that radio data, which is quite complicated. That is something that I was not willing to share. The Chinese asked for that a couple of times, but I knew that this was the thing for which they would need me also for any future mission. So that's the thing that I didn't share. And they accepted that. I mean, they tried, but I think they also respected the fact that I fought for that and they understood why. So they asked, but the answer was no. So I think, that's a long answer to your question, maybe. I think it's going to be difficult to do these collaborations, but I think we should keep an open mind and also maybe look at how the US is doing things and then compare that to China and maybe find that it's not that different.
Well, yeah, it definitely doesn't sound very easy from the way you're describing it. But yeah, I mean, hopefully we're going to see some more collaborations. We have another question from Greg, who says that he's from Japan and he worked for 3 years in Norinco. And then when he would have a problem, he would discuss it with his superiors in a very polite and respectful manner. And his question is actually, how do you communicate with superiors in Netherlands and what's different there?
That's a good question. I think the communication with superiors in the Netherlands is more direct and open. So, from my own experience, I mean, I'm a director of a lab. I have 20 people. They come to me on a regular basis, formally, informally, and it's an open discussion. sometimes I have to admit I did something wrong, or that their point of view is better, and they can convince me. So I think that is a little bit more really having discussions, more than me pushing my point and making sure that my will is done, right. And I had the feeling that in China it was more like that. It's the person at the top who decides this is what I want to do, and because of the fact of losing face, he cannot just change that opinion. So it has to happen. That's also one of the reasons why, for instance, we would hardly ever see a delay in the Chinese launch of a rocket, because it has to happen on that date, and someone high at the top, signed for that. So if that's going to change, if it's going to be later, it's his fault, his responsibility. So I think it's that. And for myself, when I go to my superiors, for instance, I talk on a regular basis with the president of our university in a very friendly, open way. Of course, he will not always agree with me, but we can, agree to disagree on certain points. So I find it's more, let's say, a level playing field compared to what I noticed in China.
Okay. Yeah, well, thanks for the answer. And I think the last one for this, at least, question break. Don't worry, everybody. I think we're going to have some more opportunities for a question. But the last one is from Ivan, who asks, was this collaboration completely independent from the European Space Agency then?
Oh, it's a good question. And the answer is yes and no. Another complicated part of this project. So originally, we got the funding to do this work through a program that is supported by the Dutch government, and it's a let's say an instrument development program in ESA, at ESA. It's called Prodex, and this is, let's say, a small program compared to the large programs where they develop, let's say, their cornerstone missions. So this is an opportunity for people like me or other scientists that have an idea, that want to build something, and that is, let's say, some budget available to help doing this. And then ESA, in addition to providing the funding and coordinating, let's say, the release of funding, they also control, or how do you say that? They check your development, and they can even provide you feedback. Now, the complication in the answer yes, no, is in the fact that it started off like this, but then came the issue that is related to our previous question, that the ESA at that point in time, if we would, finalize our work, we would deliver our instrument to ESA as part of our contract with ESA, and then ESA would have to deliver that instrument to China. And that transfer was not that easy. So that was basically, at some point, turned out to be a huge problem. So we changed that work a little bit, the way that Prodex work. And in the end, we never delivered to ESA, but we as a university, and me as a principal investigator, delivered the instrument to China. I did it actually personally in a suitcase. Of course, it's not in China, it's behind the moon right now, but so that's how it went. So ESA basically withdrew a little bit from that because it was very difficult for them to take that responsibility. So they were there, but more in the background, and certainly never with me in China.
Yeah. Oh, that does sound also really complicated.
So, I can tell you, this was not an easy project.
Yeah, I think I'm getting this feeling already.
Okay.
But I think we'll keep the other questions for the other questions breaks, and let's talk about some science now.
Yeah, let's do that. So I'm going to talk a little bit about why we actually want to go to the moon, and I'll go into a little bit detail, and don't be afraid if you can't really follow. I'll try to summarize it a little bit and give you the, let's say, the main lines on it. I think that the most important thing to realize is that we want to go into space with a radio telescope because there's a small part in the electromagnetic spectrum that we cannot see from Earth. And that's simply because long radio waves are reflected by the atmosphere, the Earth atmosphere. And you can see in this image here, where you see the atmospheric opacity, you see the, let's say, the different windows that we have on our universe, and the instruments at the bottom that we have to observe that, to observe in those windows at those various wavelengths or frequencies. So ranging from gamma rays and X-rays and UV and optical telescopes that are usually in space, also because the atmosphere blocks it. And then you have the visible light and a few other windows, infrared, submillimeter, up to microwaves, and let's say the radio window, where we have large facilities all across the Earth, even a very big one here in the Netherlands called LOFAR, even a global telescope array in millimeter wavelengths that cross that have facilities around the globe called the Event Horizon Telescope, which made that image of the first black hole. But going to larger wavelengths, let's say something above 10 meters or so, is something that we cannot see from Earth. And we have to go beyond the atmosphere, and then actually being at the moon, and in particularly being at the far side of the moon, that is very advantage. That has a huge advantage, because not only is there no atmosphere at the far side, well, at the moon completely there's no atmosphere, but at the far side there's the advantage also that there's no leakage. You cannot see the leakage from some of that radiation that still gets through the atmosphere, because the blocking is not always complete. So when you're behind the moon, you're in the moon's shadow, and this is the most quiet location where you can be. The reason why it has to be so quiet to do these observations is because the signal that we want to measure is very, very faint. So, and I'll get back to that in a minute. Now, in addition to this very, very faint signal that we want to measure that tells us something about how the universe was formed, there's also the fact that if you put an instrument behind the moon or at the moon's surface, at a location that is better than being on the Earth, you're going to do new observations that no one has done before. So you're basically opening up a new window on the universe. Now, just to give you a comparison to what we already have let's say in the radio spectrum, which we can observe. My apologies. Which we can observe from the Earth. This is, for instance, how the sky looks like at 408 megahertz. And I have even insets there of specific sources we can observe at radio frequencies. So it's quite clear that in this, sky view, you see a lot of detail, but you can even zoom in much more and see much, much more detail. So the radio, in the radio spectrum, we have large facilities. We can see long scale, large scale things, small scale things, details. It's quite good. Now, how does that compare to the radio view at these longer wavelengths? It looks a bit like this. So this is the sky observed in the, let's say, end of the 1970s with emission that lasted very shortly at about at 1.3 and 4.7 megahertz. And you can see it's rather poor. So we see some emission that is stronger in one direction than the other, but the angular resolution, so the seeing, or the resolution that you have to see the different structures, is rather poor. It's 30 degrees, which is huge. So this is the best view of the sky at those wavelengths that we had, because of this short mission that actually went behind the moon and came back, and they did this observation. That was the only observation we have currently at these frequencies, at these long wavelengths. So improving the sky map, making observations at these frequencies, is going to give you a new window of the universe. So that's an important thing to remember. So when we started off this mission, we thought about this thing, making a sky map, which is, high on our priority list. This is just a plot showing the different objectives that we had. versus the in terms of priority versus the frequency at which we think this radiation can be seen. And you can see that the low frequency sky map, which is really a science objective, is really high on the list. But you can also see that on that same science objectives there was solar burst, which happened across the whole spectrum. But of course, remember that the part below 10 megahertz was not seen before. So, that's still, you're going to see new science there from the sun. And the same goes for planetary emission that we can see from Jupiter, that is well studied at higher frequencies, but not at these lower frequencies. Then there's a few technical objectives that we want to look at or want to address once we are at this location behind the moon. And that's really related to the kind of noise that we still see at that location, because currently we don't really know. Much of the radiation that we produce on Earth in the same frequency ranges can still leak through the atmosphere, and this depends also on the, let's say, the refraction of the atmosphere, and that changes during the day. It depends on how much sunlight there is, and there's a clear day and night difference there as well. And that radiation can still bend around the moon, as waves do, and you can still maybe hear them at the moon or even behind the moon at a certain location. So characterizing that noise level is really important, and at the same time, also making a complete background spectrum, a radio spectrum. So when we put a telescope there and just listen to the universe, what does it sound like? Or when you want to make an image of that whole universe, what's the level of signal that you get? That's also quite important. But by far, the most challenging science objective, but also the most rewarding one, is what we actually call as a science potential. It's constraining the images or the signal, I have to say, from the dark ages and the cosmic dawn. And I want to go into that a little bit further. So what is cosmic dawn and dark age period? Here we see a picture actually made by the BBC for one of the series they have, which depicts basically the history of our universe, from the moment of the Big Bang to the period of the first stars that were born, a couple of 100 million years after the universe was formed, from the Big Bang, to the formation of our solar system and the present day, and even going a little bit further than let's say almost 14 billion years, that is now the age of the universe. So this is how we see the universe, and you have to remember that as an astronomer, what we do to study this history of the universe, we take our telescopes and we look at the objects that are in the sky, and because we can observe very faint objects that are far, far away, we are at that point in time receiving light from, let's say, the early days of the universe. And we can actually look back to almost the point where the first galaxies were formed. They were quite bright, they're still far away, and then we're looking at very old light because it's been on its way for a very long time. So we're looking back to that period. But beyond that, there is a period before the stars were born, and for that period there's no objects because there's no light, not from stars or galaxies. So how do we study that period before the stars were born? That's the biggest question that we have, and there's only one way to do that. Now, just remember that this period comes from the period which is about 300 to 400,000 years after the Big Bang, and this is the moment that we call the recombination, and it's that point between the recombination, which is the point where the universe was, that radiation in the universe could travel in all directions. Before that time it did not, but after that time it did. It cooled down sufficiently, and there was actually a decoupling between radiation and matter, and radiation could freely flow, and that's the, let's say, the microwave background that we have observed, for which we have a very detailed image. And the period that I'm talking about is the period between that moment and the moment of the first stars and galaxies, which is a couple of 100 million years later. So it's the period between, let's say, 400,000 years after the Big Bang and 200 million years after the Big Bang. That's the period that we call the Dark Ages, and also sometimes the cosmic dawn, the dawn of the cosmos, where the stars and the galaxies were born. That's the period that we want to study. Now, this first ever image, this cosmic microwave background, the moment of recombination, is the first light of the universe. And that was released a couple of 100,000 years after the Big Bang. And in that first light of the universe, which is like, let's say, your baby picture of the universe, you see already a lot of structures. So you see variations in the density of the radiation. And those variations in density, in the end, turned out into the, let's say, the structures that we see around us today. Because if you look at the universe today, it's not flat. It's not homogeneous distributed. You see that galaxies form clusters. There are clearly empty spaces in the universe. There are spaces where a lot of stars are clustered together, where even galaxies are clustered together. And these structures had to form from somewhere. So the question is also, how does it happen? So we can look at that recombination image, that baby image, that gives you that picture how it was. But that's just a picture. So how, from those first structures, during the cosmic dark ages, how did the universe form, and how did those first stars get ignited and form the first galaxies? Well, the answer is hydrogen. This is an image of the emission, the 21 centimeter emission from hydrogen in our Milky Way, showing you the, let's say, the center of our Milky Way, so the band where we are in, so the galaxy itself, and the outliers above it. And you see there's a lot of hydrogen in our own Milky Way. But hydrogen was the first element that was formed after the Big Bang, a very simple element. And during that period of the Dark Ages, this hydrogen was available in great abundance. So we see that hydrogen today, but we also had that hydrogen in the early universe. Now, that hydrogen has a characteristic that they can do what we call a spin flip. So the electron that is rotating around the core it can do a spin flip. This is a known effect that the electrons can do this. And electrons or hydrogen atoms around us today, they do this spin flip. This is a quantum mechanical effect. And as they do that, they lose a little bit of energy in the form of a photon, which has a wavelength of 21 centimeter. Now, that wavelength of that photon with a wavelength of 21 centimeter can be seen in emission or absorption. So you can emit at these wavelengths, or you can absorb at these wavelengths. It's just a quantum mechanical transition that you can go through. Now, hydrogen all around us today emits at these frequencies, at these wavelengths. That happens. You saw the image of our Milky Way. That's that emission. But those hydrogen atoms at the very early universe also have that effect. So they also would emit or absorb at the same wavelength. Now, just imagine for a moment that it's emitting at that wavelength of 21 centimeter. Then hydrogen that is doing that at this point in time, so all around us now, is doing that at 21 centimeter. Hydrogen that's doing that 14 billion years ago is also doing that. But that radiation, we don't see at 21 centimeter, but we see it at much longer wavelengths. And that's because that emission is part of the universe and expands as the universe expands to much larger wavelengths. And you can actually maybe see this as a picture in your mind. If you take a small balloon and not completely inflate it, and you draw a little wiggle on it, and then you start inflating it, you will see that this wiggle becomes bigger and bigger and bigger. And this is how you must see the expansion of the universe, and with that, let's say the growing of the wavelength of that emission. So what I'm saying is that the emission of this hydrogen at the very early universe, 14 billion years ago, something like that, is all around us today, but seen as at much longer wavelengths, so tens to hundreds of meters. And exactly that's the kind of radiation that we cannot see from Earth because the atmosphere blocks it. So this is the reason why we go to space, because with this hydrogen emission, we can study this dark ages period and maybe get an idea on how the first stars were born during the cosmic dawn and how the universe was what we call re-ionized again because of these stars. Now, this is quite complicated, but I'll continue a little bit more just to give you an idea on what we're talking about and how strong that signal is. So again, maybe you can forget a little bit of the details, but this is another way of looking at the age of the universe, or how the changes happened in the universe. This is a plot showing the brightness temperature, so how much radiation we get from this 21 centimeter emission at different frequencies. So this is a prediction, this black line is a prediction of the brightness of the 21 centimeter emission. And actually, when you look at different wavelengths or different frequencies, you look at different points in time, right? Because in the end, all the radiation was emitted at one frequency, and it goes to different frequencies or different wavelengths because of the expansion of the universe. So when you look at a different frequency or a different wavelength, you look at a different point in time. So you can actually use this to look at different periods during the universe. And then you can predict, as you know, or have models of what happens physically in the universe. You can predict the emission of the 21 centimeter line. And then you can see that some of the processes that are happening at that point in time in the universe have an effect on whether we see the 21 centimeter emission either in emission or in absorption. And actually, the signal that we want to see, the signal from the dark ages and the cosmic dawn, so the signal in blue and in green, are seen in absorption. Now, what we also see is that the signal in the dark ages period is quite weak, but the signal in the cosmic dawn is much stronger. So we actually think that detecting this cosmic dawn signal is going to be easier than the dark ages signal. Now, what you have to remember from this is, you can also forget about it, but if you want to remember something, then you have to realize that the shape of this curve is determined by the physical processes that happen at that point in time in the universe. And as the universe expands and cools down, these physical processes change. And they have an effect on how we see the hydrogen. So it's the interplay between the hydrogen and the rest of the universe. Now, just to give you an idea on what that does to the strength of your signal, if you change a little bit your model or the effect of a part of your model, and maybe some of the assumptions that you make. So here you see two plots above each other, where you see that there's a few things change. So we change some of the parameters in the standard models that we have that predict the shape of this 21 centimeter line. Now, you can change the amount of X-ray heating that we get from the first stars that are born, that basically can cool down the hydrogen even more, and therefore make the 21 centimeter emission stronger. Or we can see the effect of what we call Lyman alpha photons, typical radiation that's coming from stars, from large stars, that can also have an effect on the 21 centimeter emission. And you can see that changing your parameters in these models can really change the way that you see the the cosmic dawn signal. And you can see here we didn't change anything into let's say the physics for the dark ages. We just played around a little bit with the model to show what happens to your predicted signal when you change some of the parameters. But that's important to realize. Now, I'm explaining all this to you because there has been a measurement of the cosmic dawn signal. And we see that measurement here on the left-hand side, this is a publication in Nature in 2018 of a measurement that was done with an experiment called EDGES, and this is sitting in the desert in Australia, so it's not in space, and they do it in Australia because there is a small, let's say, opportunity to even observe at these low frequencies, not as low as the dark ages, but they claim at least that they've seen this cosmic dawn signal. Now, what we want to do is, of course, with our instrument, because first it's much easier to observe at these frequencies, is try to confirm this result by doing another measurement. And the funny thing about this result is that it looks to be too strong, and that the shape of the signal appears to be too broad. So on the right hand side, what we've plotted is in red the detection of the EDGES result, confirming or claiming the detection of the cosmic dawn signal, and overplotted in black and in gray are the various models that we have, cosmological models, with various parameters to make it as deep as possible, to make sure that it connects really or that it overlaps with the measurement. And you can see clearly from this is that by no means possible we can change parameters in the standard cosmological models to explain for this huge strength of this signal. And that's why in 2018 someone came up with a new model, a cosmological model, which is quite complicated to do, but they came up with an extra cooling processes, so making sure that the hydrogen gas in the universe at that point in time in the cosmic dawn was even more cooled. And if they do that, then they can almost predict the depth of that signal. Going to -600 on the image on the right bottom, you can see that -600 is more or less where the red line is in the image above. And the extra thing that you see from that is that if you want to explain this very deep cosmic dawn signal that was claimed by EDGES, you have to make a model which not only has a very strong cosmic dawn signal, but also has an enormously, almost a similar depth in the dark ages signal. So the physical thing that you had to do to your cosmos in the beginning also had an effect in the dark ages and not only in the cosmic dawn. Now, what we want to do, of course, is want to measure at these frequencies as well and see whether we can detect these signals as predicted in this model from 2018. So that's one of the goals that we want to achieve. To do that, we need a certain mission lifetime, and I can show you here. This is again a complicated plot, but maybe the conclusion from it is very important. This is the integration time or the mission lifetime that we need to either detect the cosmic dawn on the left-hand side or the dark ages more on the right-hand side. And if you want to detect the cosmic dawn with a single antenna, well calibrated, and we can remove all foreground emission. We have almost no radiation from the spacecraft that we're on, blah, blah, blah. If you assume ideal conditions, then detecting the cosmic dawn can be done in a fraction of a year. In fact, it's in the order of days to weeks if you do the calculation. And for the dark ages, it is more. It takes more time. So the mission lifetime is more than a year, almost 3 years. And now we are already in that range. So the mission lifetime for our instrument is 5 years. But I also will tell you a bit later that we haven't received all the data yet. So whether we can really detect that dark ages signal, assuming the standard cosmological models, remains to be seen. And just to wrap this up in terms of science, we have to see this whole mission that we're doing right now as a first step into, let's say, what we call a roadmap, where in the end we want to work towards having a large instrument on the moon to detect this cosmic dawn and dark ages, and then the instrument that we currently have, the single antenna, is the first step in that project, and we're working towards a larger element. And the thing for having a larger element is that what I talked to you about now, the signal is a global signal that's basically everywhere around us. This hydrogen emission from the early universe, and we just have to stick antennas out and listen to it. We have to be behind the moon or on the moon, but we can, in principle, listen to it. But that's a global signal. And if you really want to measure the signal at different stages, so of the growth of the universe, so you have to measure it at different frequencies, and then you have to map it as well, because you have to see how the hydrogen distributed itself, then you need a much larger array. And that's why we want to build a large array of antennas on the far side of the moon. And that's actually a process that we are starting with together with ESA for we're making plans for a large facility on the moon in one of the future ESA lunar missions that they're currently working on. So we're involved in that, and that's also because we are now working on that first step. So this was maybe quite complicated. Any questions on that?
Yes, I think your scientific part has definitely stirred up some questions. I think you gave us a very nice teaser into an ESA lunar base, so I think people will be asking questions about this as well. But
please go ahead.
Let's touch on some scientific topics first. So we have another question from Greg, who says, when you measure those kind of radio waves that you do, how does interference or constructive waves influence the measurement, or does it influence it at all?
Yeah, interference is a huge factor. Has a huge effect on the result. It's very complicated because let's take, for instance, the interference that is caused by other waves that we detect at the same frequencies. So what you have to do is the radio antennas that you stick out into the universe, basically, they pick up all the radio waves. So they basically have every radio wave introduces a potential difference over the antenna, which you can measure in terms of current that flows through the antenna. But you can measure the current. But every wave, the wave of your science signal, and also the wave that is produced by maybe a radio emission that's coming from the Earth, or maybe even radio emission that's produced by electronics on your spacecraft, all those radio waves are contributing to that potential difference and create a voltage or current that flows that you have to measure. And then you do a Fourier analysis of that current, and then you try to reproduce all the waves that were responsible for that current change. And then you have to disentangle signals that are coming maybe from close by, from your instrument, or from further away, maybe in a certain direction. And then you can only do that by maybe adding the signal of the three antennas, which are orthogonal from each other, and you can add them up in different ways by making the instrument as a total more sensitive in one and the other direction. So, for instance, in our case, our satellites, we are on one panel of the satellite sticking out in one side. So if we make our antennas more sensitive in this direction, we are more likely to detect radiation that's coming from the universe or maybe the sun. Whereas if we're getting more sensitive in a downward direction, we're going to see more radiation from the spacecraft. And this is actually part of what we call the commissioning or calibration of the instrument. What we want to do is to make sure that we know this pattern that's coming from the spacecraft and any other noise sources that we see. And once we know that, we can subtract it from any signal that we try to measure when we basically focus on a global signal from the universe, from this early universe, or maybe a strong signal from the sun. Then we have to also remove that noise sources. So interference and combining signals is one of the biggest things you need to do when you want to do radio astronomy.
Okay.
I hope that's clear.
Yeah, I think you gave a very extensive answer, so I think that should be. The next question is from Ivan, and he asks, is there a limit to how far you can look back?
Well, yes, because we need hydrogen, and the hydrogen was only formed at a certain point in time. I think we cannot look beyond the moment of recombination. So before the point when the microwave background was released, because radiation could not travel in all directions. There's the absolute limit to what we can see is about 300,000 years after, or 400,000 years after the Big Bang. That's how far we can see. Beyond that point, we cannot see.
Okay, so there is, in fact, a very hard limit on
yes,
looking back.
And this is a little bit maybe disappointing for people that think about what was there before the Big Bang, and are there any other universes before that time, and can we see that? Well, we can talk about all these things, and we can have even theories about it. But the point is, we can never ever see any radiation before that point, simply because of this. So yeah, it's all these theories can never be proven or disproven, for that matter.
That's yeah, that sounds like a challenge. So that's I bet that is very hard to deal with. But we have, I think, one more scientific question, and we have actually more technical questions in the chat about the satellite and the lab. But I think maybe it's nice to discuss them after the section about the instruments, since I imagine you'll cover those as well. So this also goes out to all the people who asked the question. You know, we haven't forgotten, we haven't missed you. All your questions are meticulously recorded. But I think the last scientific question for now is from Edward, and he asks, so are the results validated by other technologies, especially since you mentioned that this is a bit of a Pathfinder mission?
Yeah, it's a good question. At the moment, the only other radio instrument that has, well, not the same frequency range, or sensitivity and frequency range as we have, but goes down a little bit into our range. We go even further. Is the Solar Orbiter mission that was launched last year, on which we're also involved. That has a radio instrument, and it's traveling to the sun and doing measurements. But this was specifically designed to do measurements of the sun. So in terms of frequencies, that's the only one current mission that we can use to verify the measurements that we have. But there's a reason why we selected such a broad frequency or wavelength range that actually extends, let's say, in frequencies above the point where normally on Earth we cannot see any radiation, and that's because we wanted to have an overlap with Earth Earth-based instruments. So what we can do is do measurements that extend beyond, let's say, that break in the frequency band to the, let's say, the radio window that you can have on Earth. And then you can compare that measurement at those frequencies with instruments that we have on Earth, and we can verify that at least at those frequencies there's a match with what we detect. And then there's another angle to this, which is quite interesting. At the same mission, the Chang'e 4 mission, there's the lander on the far side. So remember, we are on the relay satellite in space, and then there's the lander on the far side. And the lander on the far side also has a radio antenna built by the Chinese, which actually looks a little bit like ours. I'm not going to say anything about that, but so that operates in almost the same frequency range as we do. And actually, in December last year, we did for the first time a measurement in parallel with the two instruments. So we observed together for at least, I think there's an overlap of 2 hours. So this way we can also use that measurements to confirm, that we both see the same thing.
Okay. Yeah, well, it's nice. The similarity in antennas is indeed an interesting fact.
Yeah.
But I think it's perhaps then a good time to discuss the actual instrument. And so let's get on with it.
Okay, good. Yeah. Mind you, again, I'm no engineer, so I can talk about science and I know a little bit about how the instrument works, but I'm no engineer. So what I'm going to talk to you about is a little bit an overview of what the instrument looks like and how we actually put it on the spacecraft, because I was present for that exercise. So the instrument that I'm talking about consists of 3 antennas that are made out of carbon fiber. They're each 5 meter long, built, as you can see on the upper right-hand side, to be orthogonal from each other in one design. So it's they have the same kind of units made from aluminium. So these units are made from aluminium, the antenna housing, and the inside is made out of carbon fiber. It actually has a wheel that you can extend and retract again the antenna. It's actually one of the things that we did during the deployment of the antennas in space, but I have a few pictures on that later on. Now, after the antennas, the next step in the chain of let's say the signal processing goes to what we call the low noise amplifier. This basically amplifies the part of the spectrum that we're interested in, and cuts off parts that we don't want to have. It's very important, this step, because this really also determines the noise level that you get from your instrument. So this low noise amplifier needs to be extremely close as possible to your antennas. So this is the reason why if this is the panel, then the antennas are sticking out on this end, and the LNA, the low noise amplifier, is close to your instrument, so that the cable is very short, so you don't have extra noise picked up by that cable. And then the next step in the processing, so the signal goes from the antennas to the low noise amplifier, and that's then connected to what we call the digital receiver and control unit, which has let's say the core of the radio instrument. That's actually the part that was built in Nijmegen and in my lab, that processes basically the signals that we get from the antennas into scientific, meaningful data. But that digital receiver and control unit also has the control of the whole instrument and the connection to the platform, the Chang'e 4 relay satellite. So it connects to the, let's say, Chinese onboard computer. And data goes from our receiver and control unit to the onboard platform, onboard computer of the Chinese, and then they send it down to the Earth using a relay dish, and I'll show that later. So in terms of some technical information, we measure full polarizations. The instrument is sky noise limited in the range 2 to 50 megahertz, which means that the only noise that we have in this design, or the noise that we have in this design, is really determined by the sky noise. So the noise from the instrument itself, caused by the cables and the whole design, is below that. So that's really important, and we choose that to be in such a way that this is the frequency range where we expect the weakest signal, the dark ages signal, to peak. So that's why we want to be as much limited in noise in that range. Now, we can in principle operate continuously, but then we need to store a lot of data as well, because the flow to the onboard computer and then through the relay dish to the ground is not continuously. So we have an onboard memory capacity of 250 gigabytes. And there's a downlink that here says it's less than 10 megabits per second, so the maximum is 10, but we never get that. And the reason for that is that the lander had this rover, and that still moves around, but it only moves around when it is day at the far side of the moon. So the far side of the moon, just as the near side of the moon has day and night, and a complete lunar day is 4 weeks, 1 month. Half of that time it is day, and half of the time it is dark. During darkness, the rover cannot move, so it needs to shut off all electronics to save power. So it's basically in hibernation mode, and that is a period of time when we can operate and when we have, in principle, a large fraction of the downlink. But in practice, it's not always 10 megabits per second. So the total power that we use for our instrument is always less than 25 watts. That's quite comfortable, I have to say, for a space mission. And we had a mass budget of about 10 kilograms, and we are just within that mass budget. You can see the weight of the antennas is 4.674 grams. And the other, let's say 5 grams comes from the, 5 kilograms come from the receiver and a low noise amplifier. So the heart of the instrument, as I said, was made at Radboud University, actually in my lab, by my team. It consists of a software-defined radio system, an SDR. We first originally thought to either build that ourselves, and we actually have now, but at that point in time, the time was quite limited to do that. So we considered off-the-shelf options. One off-the-shelf option was from an institute in Poland, but it turned out not to be, in terms of performance, not good enough. And therefore we went to a commercial solution from a company called SCS Space in South Africa, and they had built this SDR to do data processing for an instrument that was actually going into space. At the time when we bought this receiver, or this part of the receiver, this SDR, their instrument was waiting on the launch pad to be launched. So when we bought it, it was not space proven. A month later, it was. We actually programmed that whole SDR board ourselves. So we removed the software and put on our own software. That's what we did together with my team and the team we hired also another company to do this who have a lot of experience with that. Then you have the ADC board, analog to digital converter. That's the thing that we built ourselves, we designed ourselves, and we got some help there from the Space Research Organization, ESON in Utrecht, to do the final production. As we don't have any clean room, this production was actually done at ESON. And the same goes for the backplane. That's the plane that actually connects the SDR to the ADC board. As the SDR company, SCS Space, did not have an ADC at that point in time, and they're actually now quite interested in buying that option from us. So that's it goes both ways. The whole complete housing was also designed and built in our lab in Nijmegen. Now, I hope you can see this movie, but what I show here is the time-lapse final integration of the flight hardware, as it was done in a clean room at the company ISIS, one of our main partners in this project, who did the integration of the whole system, and also had the onboard computer, the control unit that they're working on. As you can see right now, it's a stack that is actually cube size, and the reason for that is that this company is used to build CubeSats and deliver CubeSats, complete solutions. So that's why we work with them, because they have a lot of experience with this. And so this is the way that we, in the end, integrated the whole system. And as you can see, they're going back and forth on the same part for a long time. And this is because this was the actual flight hardware. So you had to be 100% sure that every connection was okay, and that it was working, and then you have to glue it and make sure it's tight and do all kinds of tests. And this is a little bit how you see that process went. In China, I always make the joke that this time lapse is played in real time, so not sped up, and this is how fast we can actually work. The Chinese were quite impressed with the fact that we were able to deliver and to design and build this whole system in less than 2 years. So just to show you a little bit how the antenna deployment goes, So this is a test of a functional test of the flight system. So these are the flight models for the antennas. You can see the crates in the background. This is not a clean room, it's more an engineering workspace. We only wanted to test here whether the antennas could be deployed and whether the commands could be given from our hardware, from our electronics, to make sure that the antennas could deploy. So this was the final functional test. Actually, as you can see, there's one of these Pelly cases standing in the left corner of this room. That's a Pelly case I took to China the next day. So this was on a Friday evening, and the next day I took this Pelly case with the antennas and brought it to China together with the system engineer, and we delivered it and mounted it on the spacecraft. But the actual deployment in space went in more or less the same fashion, although we experienced some problems. So at some point we had to pull back the antennas a little bit and push and try again. Yeah, so now we get to the more maybe more spectacular or exciting images of the clean room in China. Now you have to remember that I think I am one of the first Westerns to be in a Chinese clean room, and so close to the actual spacecraft. So this was quite a big room. I think it's about, well, was it 20 by 20 meters and some 15 meters high. In one corner of the room there was the spacecraft. In the other corner of the room there was the relay dish that was later mounted on top of the spacecraft. And in the far end of this room was a panel, which was almost empty. And this was that panel, that was the panel where we were going to mount our instrument on. And here you can already see, this is almost when we're almost done. So this is the inside of the panel, where you can see on the top, on the left-hand side, you see on the top the LNA, the low noise amplifier, and at the bottom you see our control unit and receiver unit. And the antenna system itself is on the other side. Now here you see the panel a little bit more from edge on the side, so you see the antenna sticking out. And I'm actually here working on a check. So the system engineer was standing there with his cap tilted in the back. He actually connected all the cables and did all the tests. But at some point, someone has to check all these connections and make sure that they're correct and no mistake is made. So there are all these labels on these cables, and you have to make sure that you have the right one. There's a special order to do this as well, a special sequence. So I did this check. I was actually allowed to touch the hardware at that point in time, which was quite special. But you can see the Chinese are really on my back all the time, checking what we're doing. At some point, this panel was mounted on the actual spacecraft, and this is before they put on the insulation material, this gold foil. So on the panel it's not there. You can see it's placed on the antenna unit itself. And during this image, you can see that the antennas were deployed for almost 0.5 meter. And this was the functional test, the final test that was done in the clean room. So these commands to deploy the antennas were at this point in time given by the Chinese onboard computer. So we were not in control anymore. This was an end-to-end test and a check whether the onboard computer of the spacecraft was able to communicate and operate our instrument. And it received data, and we have that data actually. That's an important test as well. So this was a final check and a final okay to proceed to the launch. And this is a month before the actual launch. So here you see a more complete overview of the whole system, still without the multi-layer installation mounted on the panel of the spacecraft body. But on the top of this box, you see the folded relay dish. So this is now folded up, and it was only deployed when the spacecraft entered into the orbit. at the Earth-Moon L2 point, the second Lagrangian point, and then it folded open like this. And this is the antenna that is used for communications. And as you can see, it's quite close by to our antennas, and it just about fits. If we roll out our antennas even further, they just, there's some clearance with this relay dish, but it's not a lot. It's quite exciting. So this is the final mounting of the spacecraft. You can see it's being towed on the rocket fairing. So this is the unit that holds the payload of the rocket. So this is the nose cone basically of the rocket, and you can see our antennas are completely deployed again, and now all the foil, the insulation is being is attached to the spacecraft. And what you can also see on the left hand side, and you see it also a little bit on the right hand side, are the folded solar panels that would open up once in space to give the instrument and the whole platform power. Here you see a close-up of this of the deployment test that we did, and you can actually see the shape of the carbon fiber antenna and how it extends. And this was actually a retraction moment. It went back in, but you can't see that, of course, in this picture. But so this is how we designed the antennas, and the fact that it is so curved is because the carbon fiber is quite stiff and lightweight. But in order to keep it in its shape, even when there are vibrations and other movements, so you can imagine that the spacecraft can be accelerated, and that can have an effect on these antennas. But in order to prevent it to buckle and bend, we make it in this shape so that it's more rigid, and it cannot do that. And in the end, it turned out that to keep the antenna in this shape, we had to have a special element mounted on the end, on the tip of the antennas, to maintain its shape correctly, and also to allow for smooth deployment and even retraction of the antenna. Well, this is a quite unique image that I didn't take myself because it was not allowed. This is I think one day before the launch, where they did a test of opening up the let's say the housing of the rocket. You see a lot of military personnel walking around, but this is how close I could get to the rocket just before the launch. And just as a reminder, this rocket is filled with fuel to almost the top, where you see the red flag on the top. That's the fairing of the rocket, where the antenna, our antenna, and the spacecraft is in. This is the morning of the launch site, and I'm showing you this picture just to give you an idea of how that was. The launch site in Chichang is close to the Nepalese mountains, so it's already quite high, and the launch site is in a valley, and we were just, I think, 1.5 kilometers away from that launch site, higher up in the valley, looking down. And then you can imagine that the sound that you get from a rocket launch like this is overwhelming, because it's basically well, even enhanced by the shape of this valley. So that was quite a spectacular moment to witness, and I would say once in a lifetime thing. Here we have some animations of what happened to the let's say to the instrument after the launch. So at some stage the payload is released, and then solar panels are deployed, and even the relay is deployed. So what I said just now is not really correct. So I think maybe the relay dish was deployed before. I'm not 100% sure actually about that, but maybe it should be, because there had to be communications. But at least the thing flies to the moon on itself. So the most of the rocket is actually thrown away, and once you leave the Earth orbit, the whole instrument flies by itself on its own propulsion. In addition to this relay satellite that was launched to the moon in May 2018, there was the landing on the far side with the rover, and, well, first the lander, of course, And here you see this happened in early 2019. You see the first meters of the little rover U2, U22, I have to say, that is actually up to today still moving around on the moon. This is the picture that the rover took of the lander, and here you can, if you look closely, you can see three antennas sticking out almost in a plane equal to the height of the lander. So let's say parallel to the ground, and you can see the shadow of those three antennas on the left-hand side on the ground. So this is the radio antenna instrument that they have on the lander. The antennas itself are a bit different to our design because I think because we didn't release our design to them only at a very late stage. The inside of the spacecraft, or the inside of that instrument, how that works and the kind of operations they have is quite similar to what we have, which is not a problem. I think there's only a few ways in which you can do this kind of science. So that's quite interesting, and we're hoping to get simultaneous observations out quite fast. Well, this is a panoramic view of the lunar far side. This is the side of the moon that you never see, so this is quite spectacular. I think it's an image taken from on top of the lander, and here you can see one of the radio antennas, and maybe even the second one as well. So this is quite a impressive image, especially when it was released for the first time in 2019. This is the part that we've never seen. So the Chinese are really breaking new ground here for us. Myself, I was quite proud to get this image. This image was taken with a camera on the spacecraft when the whole spacecraft came into the correct position behind the moon. So it's now some 64,000 kilometers behind the moon. There were a few cameras on board of the spacecraft to also do make some interesting pictures for PR purposes, of course. Luckily for us, here you see actually the moon and the Earth together in one shot. Luckily for us, our antennas were not bigger, otherwise we would have blocked the moon completely in this image, which would have been a shame. But what you can see, the moon is in the center here, which is the objective which is closest at this point in time, and the Earth is in the background, and you can see sunlight from above. In the image, you probably recognize one of the antenna elements, so we can only see one of the three elements here. And the other thing that you see in this picture is the relay dish on the top part of this image, where you see sunlight coming through the mesh of that relay antenna. These are images that were made in November 2019. So it took a long time for us to do this deployment. This is the deployment of the antennas, and it took a long time for us to do that because the success of the rover running around on the far side of the moon was bigger than they anticipated, even in China. So they wanted to keep operating that and pushed our operations back for a very long time. So we were only allowed to deploy the antennas until late 2019. This was actually the last trip that I made to China because of COVID that happened after that. So I can still remember this one, but it was the last time when I went. And you can see here the various stages of the deployment of the antenna, and especially for this unit, you can see it deployed to almost a full 5 meters. If you look at the image on the right, you can actually see the reflection of sunlight on the two other antennas of the whole unit, and you can see small little white lines on the right hand side of the image in the middle, and also at the bottom you see a very little white maybe light white line, and these are the reflections of the other three antennas. So we have visual confirmation that the antenna is deployed. I have to say that we had some technical issues during the deployment. And at some point, I think we had to stop the deployment because we weren't sure about the situation that was happening, and we were a bit afraid that we would destroy some of the hardware. So I think one antenna is then deployed to almost 5 meters, and the other two are, I think, a meter less. That's not a real problem for our science. So the approach here is to do some first science, and that's what we're working on right now. We're actually waiting for new data to come in 1 or 2 weeks. And after we've done that science and maybe come up with a few results, we're going to try to push the other two antennas to the full 5 meters as well. So this is just a final, let's say, mechanical thing we want to try and do to show that system, also to test that antenna deployment system, because it's unique. It's the only type in the world that can do this with carbon fiber. So we want to test and see how that works. So I think that's a little bit my story. I hope you liked it, and if there's any other questions, then please let me know.
Yeah, well, thank you for the nice presentation. I think it was actually a very, complete one with all the, engineering, scientific, and cultural aspects. So I think that really covers the entire mission. But indeed, we do have some questions. So I think there's one question from Sebastian, but I guess he would need to clarify what the question is about. And Sebastian asks that now that the mission is deployed, did the lab turn back into a yoga classroom?
No. Okay, I'll explain that. So the when we started the radio lab in end of 2015, actually just before we got this opportunity to do this, we had let's say office space to work, but no official lab, and we actually didn't got any funding from the university to have that. But as soon as we got this this mission opportunity, I suddenly realized, oh my God, we're going to build an instrument. We need a secure room to do this, and this equipment is, very expensive. So it needs to be very safe, and has to have all these certain conditions. So I'm going to look for a lab space. So I did that, and in the end, it turned out there was one room that was being used by yoga classes. Don't ask me why, but the director of the faculty said to me, "Well, Mark, I think your project has a little bit higher priority than yoga classes, so I can clear the room for you." So he did that, and a week later we could move in. We're still there, but looking for a bigger space.
Yeah. Do you know if they have successfully relocated somewhere else, or is there no yoga anymore?
I don't know. I actually don't know. I never heard about that anymore. I assume they went somewhere else. I hope. Well, I have nothing against yoga. I don't want to step on anybody's toes.
Yeah. In this case, science prevailed over sport. So.
Yes.
And the other question we have from Jesper, and he asks, in what kind of way do you receive the data? So is it streamed continuously back to Earth, or is it transmitted in batches? And were there any challenges in sending data from the other side of the moon?
I think the biggest challenge in sending data from the other side of the moon is called the Chinese firewall. So I would actually think that getting the data to the ground is a relatively easy process. I mean, the Chinese have ground stations in China, a couple of them, and even one in Namibia. So they can almost continuously download data. But then getting it from China to the Netherlands, it goes through a military system. So one military high official has to approve every package of data that we get, and that is a long and cumbersome process. So that's not very smooth at the moment. But to give you, but to try to give an answer to the first question, so we don't get continuous data. We could, I mean, in principle, we could observe all the time, and that would be ideal. But of course, we are limited already to half this month. And then what actually happens is also because of technical issues and how commands could be uploaded to the spacecraft. Most of this actually had to go by hand because of a technical issue on the platform side. So because of that, we only observe every now and then. So we have sequences of observations, and they are stored in our buffer, and then we have another buffer on the Chinese side. So it comes down in batches. The Chinese then collect it on their ground segment, and then they provide it to us, and then we analyze it. So up to now, we have about, I think, 100 megabytes, a few hundred megabytes of data, which is not a lot. And there's a lot of other technical complications, and one I think which really had a huge impact on this whole mission and also on the data that we received, or actually that we didn't receive, is there's a communication problem. So not in terms of Dutch and Chinese, but the communication between our instrument and the platform has an issue. And we had to skip a few tests before we delivered the flight hardware. We actually mounted the flight hardware on the spacecraft. So some of these tests were not completely done, and I think that was a mistake to do. We didn't have time, so there was no other way. But the result is that we every now and then, during the transfer of data from our instrument to the onboard computer, there's an issue on the CAN bus, and the CAN bus is doing the communications of data, so the flow of data from one instrument to the other. And the result is that there has to be a reset of this CAN system, which is not ideal for operations, because there are other instruments on that same CAN bus that Chinese instruments or that are part or essential to the spacecraft. And because we were not able to go back to China to take our lab equipment or our lab setup and connect that to a lab setup of their instrument and just do another interface test and try to find this issue and try to solve it, we were not able to do that because of COVID. For almost a year, we were not able to download lots of data, just a little bit of it. And only recently we found a way around this. So on our end, we did a lot of testing in our lab, and at some point we found a solution to this, and we suggested that to the Chinese, and that was actually implemented, and that seems to work. So that was tested in December and in January. So December last year and January this year, and that data, which is actually quite much more data than we ever got before, is now in a ground segment in China somewhere, waiting to be released to us. Sorry, long answer again.
Yeah, no, but it's good. It's good. I think it's quite interesting that the biggest challenge is actually Earth-based problems rather than sending data from thousands of kilometers away.
Yes.
And I think the last question for today, because we've went a little bit over time, is from Dmitry, who's asking, do you believe, as someone who is involved with the space industry, that it is possible to move people to other planets, especially maybe given the recent Mars hype that Elon Musk is giving it and the landing that's happening later today?
Yeah, the landing is actually happening in less than, I think, in an hour or so, or even less than that. Yes, I believe it's possible. I can talk a long time about this, but I think it's possible, and we're moving very fast towards that, I think. So I think we are going to witness that, especially to the moon. I think that will happen maybe in the coming, maybe 10 years, 10, 15 years, perhaps a bit longer, but I think we can witness that. To Mars, that may take a little bit longer, but especially once we have landed on the moon and we put humans on the moon, I think the next step is going to be Mars.
Okay, well, that's good to hear some optimism, I think.
Well, you heard my story on the project. I have to be optimistic, right?
Well, good to hear anyway. But
Yes.
I think this is going to be the last question that we take. And from my side, thank you very much for giving this talk. I think it was really insightful, and from what I can see in the chat, people also enjoyed it quite a lot. So
Thanks.
I hope you also enjoyed your time here. It is, of course, a
I
bit
did.
of an unconventional lecture talk,
Yes.
but we have to make do, and hopefully, in some times we can organize a physical one. But
Yes.
yes, in any case, thank you very much to you, Mark, and thank you to all of our viewers that attended. Just as a side note, before we completely shut off the stream, if you join the Space Society 20 Discord server, links in the description, we will be hosting an impromptu landing watch party for the Mars rover, and I think we finished just in time to do that.
Yes. I hope I didn't steal too much time for that.
No, I think we're good on schedule. So,
Good. Thanks. It
yes,
was my pleasure.
great. Thank you, everybody, and we'll see you later.